Chapter 5, we'll learn about solutions and aqueous reactions, and the quote here is from Karl Popper. Science may be described as the art of systematic oversimplification, the art of discerning what we may with advantage omit. I don't remember why I don't have any slides for section 5.1. You should read it. I think it was interesting, but didn't deserve space in lecture, so I skipped that one. So solution concentration. Chemical reactions often involve reactants that are dissolved in water. These are very common and important, and so that's what we're going to learn about. So a homogeneous mixture of two substances, such as salt and water, sugar and water, is called a solution. So a solution is a mixture, but it's homogeneous. So there are two parts to solutions. There's the solvent, and then you can have one or more solutes. The definition of which is which can be confusing in some circumstances, but in general, the solvent is what there's more of, and the solute is what there's less of. In an aqueous solution, the solvent is always water. So you can have one solute, you could have two solutes, you could have a whole bunch of solutes. So if you think about taking a glass of water and putting a teaspoon of salt in it and stirring it up, the water is the solvent and the salt is the solute. It's dissolved in the solvent. Then you could take a teaspoon of sugar and put it in there and stir it up. Now you've got two solutes. You've got two different things that are dissolved in the water. We have quantitative and qualitative descriptions for how concentrated or dilute a solution is, how much solute is in the solution. So qualitative description would be dilute or concentrated. And these are relative. If I say, well, that's a dilute solution, that doesn't tell you exactly how much is in there. And that might be dilute to this other more concentrated solution, but it might be more concentrated compared to one that is more dilute. So those are just, general terms. Here are the pictures. In this one, we've got a lot of solute present in the same amount of solvent, and here there's just a little bit. So this is like concentrated frozen orange juice, right? And to make it into orange juice, you have to add water and dilute it, right? Because the concentrate is just way too strong, right? Of course, in chemistry, we really want to be able to quantify how much solute is present, and the most common solution concentration that chemists use is molarity. And the abbreviation for molarity is a capital M. There's just a lot of M's among those units. And this is the definition for molarity. Molarity is the amount of solute in moles divided by the volume of solution in liters. And so the units of molarity are moles per liter. We'll see some other concentration units where they talk about the volume of the solvent, but molarity is the volume of the whole solution. So this slide shows an illustration of how to prepare a solution of a specific concentration, and you'll be doing this in experiment, I think it's 5B, that's coming up. So this piece of glassware is called a volumetric flask. And kind of like a volumetric pipette, it is designed to accurately contain only a single volume. So there is a mark on the neck, And so this is a 1 liter flask. If you fill it up so the bottom of the meniscus is at the mark, you've got 1 liter in your flask. You can't measure any other volume with that. But this is convenient for making solutions because now you know the total volume of the solution. So what you do is you put the solute in first. If we filled this up with water first and then put the solute in it, the solute would displace some of the water and the total volume would be greater than 1. So we have to put the solute in first. It would also be really, really hard to mix if we put it in afterwards. So here we're making a 1 molar solution. 1 molar has nothing to do with teeth. That's 1.00 moles of sodium chloride per liter of solution. So measure and weigh out 1 mole of sodium chloride. So that would be 58.44 grams. A lot of times you need a funnel to get it in there. You've weighed this out very carefully. You don't want to spill it because then you have to start over. So you get all your solid in there. And then you're going to add water. You're not going to fill it all the way up because you need to get that salt to dissolve first. So you want to fill it, I don't know, half to 3/4 full. And then you're going to put a stopper in it, and you're going to invert it, and you're going to shake it around until you can't see any solid in there anymore. Then you know it's all dissolved. Then you go and you finish adding water until you get the bottom of the meniscus right here at the line. Then you put the stopper in again, and we typically hold it with our thumb over the stopper, because you can imagine we're going to tip it over. It'd be really sad if the stopper fell out and our solution spilled, right? Because, again, then we have to start over, and it's not fun. So you hold it with your thumb, and then you invert it until the air bubble goes all the way to the top, and you turn it up again. And you do that like 10 times. There's a little video in the Helpful Videos page that shows how to do that. Any questions? So how many moles of solute are needed to make 3 liters of a 2 molar solution? So anytime you see this capital M, students often forget what that means. So this is 2.0 moles per liter. It's just that's easier to write, so everybody does that. So if I want to make 3 liters of a solution that's 2 moles per liter, how many moles do I need? 6, right? 3 liters times 2 moles per liter, the liters cancel out, and it gives me 6 moles. So molarity, we're going to find out, is another very useful conversion factor. So that's, oops, wrong slide. Any questions? So let's calculate the molarity of a solution made by adding 45.4 grams of NaNO3 to a flask and dissolving it with water to create a total volume of 2.50 liters. So there's no question word, but there's a command, calculate the molarity. And then they're giving us a mass of NaNO3 and a volume. Calculate the molarity. Calculating the molarity, like calculating the density, you're going to use the equation. So molarity, capital M, equals moles divided by liters. That's the short version. So I need to know how many moles of solute I have. Did they give me moles of solute? Of course not. That would be boring, right? They gave me grams. Can I convert that to moles? Yeah. So I'm going to have a conversion down here. I'm going to take 45.4 grams of NaNO3, and I'm going to convert that to moles of NaNO3. And what do we use to do that? The molar mass. So following our path here, I've got grams of this. I'm just going to have a single factor here. This is moles of NaNO3 and grams down there. And so I need the molar mass. So we go to the periodic table and look up sodium, 22.99. And then I've got nitrogen and 3 oxygens. So my calculator shows me 85. How many sig figs does that number have? Well, as it's written, it has 2. But how much should the result of this calculation have? Should have 4, because these guys all have 4 sig figs. I'm not converting this yet, then we'll end up with 3. So just, to not mistake that for an exact number or for something with 2 sig figs, I'm going to put those significant figure zeros in there. So remember that molar mass is the mass of a mole. Somebody was getting theirs very consistently backwards, which is better than random, but very consistently putting the number with moles and 1 gram, which unfortunately gets you a lot of wrong answers. So molar mass, mass of a mole, right? So we have 1 mole, and the mass that we calculate is 85.00. So then I've got 45.4 divided by 85. And this one's going to have 3 sig figs. 3, 4, and that's, nope, not grams, moles. I want to keep 2 extra digits because I don't want to have any rounding errors. So this is my moles of the sodium nitrate. So I can plug that into my equation up here. 0.53412 moles. And what's the volume? 2.50 liters. Sometimes they'll give you the volume in milliliters. Molarity, it has to be liters. It has to be solute in moles, volume in liters. So we divide by 2.5. 0.21365 moles per liter. So rounding to 3 sig figs, we get 0.214. And you can use the capital M. I try to make my capital M's pointy so they don't look like an overgrown meter. Or you can use moles per liter. Any questions? I think one of the common issues I see even with students in Chem 1B, so these are students who successfully passed Chem 1A, they come to Chem 1B and they see this capital M and they think moles, which is kind of half right. It's moles per liter. And it's, confusion's understandable because we have moles and we have molecules and then we have molarity. There's just a lot of mole stuff, right? So the capital M is moles per liter. So as I mentioned, the molarity is a very useful conversion factor between moles of solute and liters of solution. So if we have a 0.500 molar sodium chloride solution, that means we have 0.500 moles of sodium chloride for every liter of solution. So we can write it this way. 0.500 moles over liters, or we can write it upside down, liters over 0.5 moles. Because for this solution, 1 liter is equal to 0.5 moles. And so we can convert back and forth between volume and moles. So here's an example of that one. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? So again, it's a good idea to go into the problem and identify what you're given and what you're asked for. So here I've got 1.55 liters, and it's 0.758 molar sucrose. And what's the question? How many grams of sucrose? So I'm trying to find grams of sucrose. So I've got two numbers there. I'm going to write both of them down. 1.55 liters and 0.758. Don't write the capital M, because then you'll be trying to cancel capital M and nothing else is going to have a capital M in it. Capital M is an abbreviation. It's shorter to type into a computer than moles over liters. So when you write with your hand, that doesn't really matter. So you want to write this, like we did with density, as a vertical fraction, moles per liter. If we write it like this, then a lot of funny things happen when you try to cancel those out, because your brain doesn't recognize that this is in the denominator. And so all kinds of strange things happen. So just make it a vertical fraction. And we're trying to find grams of sucrose. I'm going to use its formula. So one of these is our starting number, and one of them will be something else. So we want to look at which of these could possibly be a conversion factor. The molarity, right? This relates to different units. It's got per in it. So like 99.9% of the time, you're not going to start with that one. You're going to start with the other one. So we're starting with the volume. So now we come up with a path. How am I going to get from volume of solution to grams of sucrose? Just like with stoichiometry, there's often going to be moles in the middle. I can go from liters of solution to moles of sucrose using this concentration. Can I go from moles of that to grams? Yeah, I just need the molar mass, which they didn't give me, but I have a periodic table and a calculator. So this one has two factors because it has two arrows. 1.55 liters times in a line, and here we want to go to moles of sucrose. And then we want to go to grams of sucrose. So I want to divide by this unit, liters, and then here I want to divide by moles of sucrose. I graded worksheet 3 this weekend, and most of you did really well. What I observed is when you write it out like this, you're much more likely to get it correct. The ones where I saw little scribblings without any units, that's where often something went wrong. Because without the units here to identify things, it's really easy to divide instead of multiply, or multiply instead of divide, and mess things up. And so, yes, you can do it without writing this down, but do you want to get it right? Just try it this way. So moles per liter, that was this concentration that was given. And again, pay attention to, here's the number, what unit is it with? It's with mole. So it goes with mole here. Sometimes it'll be on the top and sometimes it'll be on the bottom. But the unit tells you where to put it. So here it goes on the top. I should cancel out my units. Those guys cancel. That big guy cancels that big guy. And then we need a molar mass, right? 12 times 12 and 22 times 1.008 and 11 times 16. I also saw a lot of mistakes on molar mass calculations, which is really understandable because there's a lot of numbers here. And if you're doing it just thinking about it, it's easy to skip something. So again, I'd really encourage you to write this down and then go through it on your calculator. And then if you really want to be sure, try it again, because sometimes your finger doesn't do what your brain tells it to do. So this is giving me 342.296 grams. So that's the mass. That goes with gram up here. 342.296 grams is 1 mole. So in evaluating significant figures, both of the numbers that I started with had 3. This had more than 3, and so my answer should have 3 sig figs. I'm going to write down 2 extras, because that's what I do. And then we'll say this is 402 grams. Any questions? This is the sort of a problem you might want to do if you were trying to make 1.55 liters of a solution with this concentration. You have to calculate what mass of the solute do I need to weigh out. Any questions? This is another example of one of those really, really important calculations in chemistry. So if we dissolve 25 grams of salt in 251 grams of water, what is the mass of the resulting solution? So our choices here are 251, 276, and 226. Yeah, it's going to be B, because the water by itself weighed 251 grams, right? So it can't be this one because we're adding something else in there. And even if it dissolves and seems to disappear, its mass doesn't disappear, right? So it can't be that one. And it can't be this one because adding something doesn't make it lighter, it makes it heavier, right? This is one of those questions. I mean, it threw me for a loop initially because I'm like, wait, what? Because it's like so different than what we were doing, right? We're like, oh, well, we have to convert this to moles and stuff and do this and that. Oh, no, it's actually just asking us a very simple conceptual question. This reminds me of the problem on the worksheet about how many atoms were in 1 mole of B12, right? And that one freaks everybody out. It just does. So you're like, wait, we didn't do anything like this. And so answers varied. I got a lot of Avogadro's number, which I understand. but those are molecules, right? And so a mole of molecules is 6.022 times 10 to the 23rd. But how many atoms are in each molecule, right? So that requires you to put some things together in a different way, and that's the kind of thing that will show up on exams. Oftentimes, we keep solutions as concentrated solutions. We call these stock solutions. We keep them in the stock room. They are in stock, right? And this is a little bit like going to the grocery store or the convenience store or whatever and buying a concentrated cleaner and bringing it home and diluting it into the spray bottle. You add some water, and it just saves a lot of money because they don't have to transport all that water all over the place, right? The container can be smaller, but you still get all the cleaning power. So we do that to save space and also because it's more convenient. So we can dilute the solution, and the math actually is much easier than trying to make a specific volume starting with a mass, because here we don't have to do any molar mass conversions. So we take some of the concentrated solution and we add more solvent. This is like taking that frozen orange juice, which, really, in this area, you should be drinking fresh orange juice, but whatever. But you take the frozen stuff, right, and you put it in a pitcher, and then you add water to it, right, and you mix it up. The volume has gotten bigger, right, and the concentration has gotten smaller. Did the amount of orange goodness change? No. It's just spread out over a bigger volume now, right? We diluted it. And so that's the idea here with diluting solutions. The amount of solute doesn't change, only the volume of the solution changes. If we have solution 1 with a certain number of moles of solute, then our diluted solution is going to have the same number of moles. And so because of that, we have this equation. That's not a highlighter. M1V1 equals M2V2. So if we think about this, that capital 1 is molarity. So that's moles per liter. And multiplying by the volume in liters gives us the moles of the solute, right? And over here, the molarity is different and the volume is different, but it's going to give us the same number of moles. So M1V1 equals M2V2. Here's an example of making a diluted solution. So here they're making 3 liters of 0.5 molar calcium chloride from a 10 molar stock solution. So if we want to do the calculation to see how much we would need with M1V1 equals M2V2, that's the molarity 1 times volume 1 is equal to molarity 2 times volume 2. This volume and this concentration go together, right? This volume of that. So maybe let's call that 1, right? So this is volume 1, and this is molarity 1. And then this is the other molarity. So that's going to be molarity 2. So here's my equation, and I'm trying to find the volume so that I know how much of my concentrated solution to put in there. So what I'm trying to find is volume 2. I have volume 1 and molarity 1. I have molarity 2. I want to know the volume. So I have my equation, and then I'm going to have to rearrange it. So if I divide both sides by M2, then I get V2 by itself. V2 equals M1 V1 over M2. Well, M1 is 0.5. And volume 1 is 3 liters. And that's going to be divided by molarity 2. So 0.5 times 3 divided by 10. 0.15. So we'll measure out 0.15 liters of that stock solution. We'll pour it into a flask. This is going to be a 3-liter flask because we're trying to make 3 liters. And then we're going to add solvent, here water, to this concentrated solution until we get to the mark on the neck of the volumetric flask. And again, we need to stopper it and hold that stopper in and mix it very thoroughly. Down here, what they're trying to show you is that if we take the volume of the first solution and its molarity, and we calculate the number of moles, we get 1.5 moles of solute of calcium chloride. And here's the concentration of the second solution and its volume, and that gives you also the same number of moles. The moles of solute isn't changing, we're just changing the volume. Any questions? So let's do a practice problem. To what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.75 molar calcium chloride solution? Well, again, let's pull out those numbers. And then what are we looking for? We're looking for a volume in milliliters. And we have this word here, dilute. That's not what I meant to do. The problem with the dilution equation is that students like it too much. And so you try to use it when you should be doing stoichiometry. And unfortunately, there are people out there that teach students to do that, and it's a really, really bad idea. So we're only going to do M1V1 equals M2V2 when we're actually diluting something. So here we have that word dilute, and we also have the same chemical that we're starting with and ending with. This is not a chemical reaction where we're trying to figure out how much calcium chloride would produce this much calcium or chlorine gas or something. It's a single compound, and we're just diluting the solution. So we can use M1V1 equals M2V2. So M1V1 equals M2V2. Move that. So then let's identify what our given things are. Again, it's this volume of this solution. Those guys go together. You can call those solution 1 or solution 2, doesn't matter. But you have to pair these guys together. We came across those first, so I'm going to call those 1. So this is volume 1, and this is molarity 1. Then this has to be molarity 2. And I'm trying to find volume 2. So I'm trying to find volume 2. I have this equation. It's best to rearrange it when you still just have variables instead of getting all these things and their units in there and then trying to rearrange it. So rearrange it first. And if you are one of the many people who does not like algebra and you can't quite remember how to do this, please come and ask me, and I can help you with that. Because we are going to be doing this kind of algebra a lot, and it won't take you but a couple of minutes, and you'll remember how to do it, and everything will be great. So the thing about rearranging equations, this side is equal to that side. It's kind of like a teeter-totter. It's balanced. And so we need to keep it balanced. We need to keep it equal. So if we do something to one side of the equation, we have to do the same thing to the other side of the equation. So I'm trying to separate V2 and get it by itself. I need to get rid of M2. If I divide this side by M2, M2 over M2 is 1. It cancels out. But if I do it to that side, I also have to do it to this side. Okay? And it's super easy to mix up your 1s and 2s. So write it down and look at it carefully. And then copy it down again. So the thing we're finding, V2, is equal to M1, V1 over M2. And make sure, okay, that was 1 and 1, and 2 is in the bottom. Okay. So now we can put our numbers in. So M1 was 5 molar. So 5.00, and that capital M means moles per liter. And this volume is 100 milliliters. And this volume here in liters and milliliters, those aren't going to cancel each other out, but it's okay because we're going to put something else in the bottom here. So molarity 2.750 moles per liter. The milliliter here doesn't cancel this liter, but moles per liter and moles per liter cancel each other. If you want to convert that into liters because it makes more sense to you, go right ahead. But then at the end, you're going to have to convert back to milliliters. Okay, so we have 5 times 100 divided by 0.75. It's kind of a scary number. Just a lot of 6s. And what's the unit? Milliliters. The line above that digit means that that digit gets repeated. If you underline it, in most chemistry circles, that means that that's your last significant figure. So how many sig figs should this guy have? 3. So that'd be this one. And so we can do 667. 666 makes me think, yeah, the devil called, he wants his weather back, right? 113 today, ugh. Anyway, 667 milliliters. Any questions? 115. 115? Mm-hmm. Nice.
I gotta crack an egg on the street.
You probably bake cookies on the dashboard of your car. At least your car would smell good. But any questions? 667 milliliters.